Welcome back to Introduction to Predicate Logic. I'm McMaster Kapoor and this is Discrete Mathematics with Applications 2 at McMaster University. In the previous video, we talked about logic and things we can do with it. In the second part of this lecture, we talk about different levels of expressiveness in logic and when is suitable to use which one of them. The simplest and most abstract form of logic is propositional logic. The formulae here only include atomic propositions and logic connectives. It basically is a way to translate a system down to Boolean level and then be able to reason about it manually or with automated processes that translate these formulae to pure Boolean values. As for its syntax, any well-formed or acceptable formula of propositional logic contains only proposition constants, which are sort of the underlying alphabet of symbols we use to express formulae. If we define atomic propositions as statements made from symbols that must be true or false, then any propositional formula is inductively built from atomic propositions and logical connectives, which are logical and and or, implication, negation, and equivalence. What we call a language is basically the set of all the well-formed formulae that we can build from proposition constants and following the rules that we have in the syntax. Now, semantics. The interpretation of a language is basically the way that the words of the language are mapped to the things in the world we are modeling. And in the propositional logic, everything defined by the signature of the language are mapped to either true or false, depending on the truth value of the atomic propositions that define them. So if we have two formula psi and phi, and they are both well-formed formulae, everything that you see on the left, that I'm showing with cursor basically, are well-formed formulae as well. And their truth value is defined as you can see on the slide. So for negation of phi to be true, phi itself should be false. For the and of psi and phi to be true, both of them must be true. For their or, on the other hand, only one of them at least should be true. And for the implication from phi to psi to hold, we need psi to be false. So basically, whatever we have on the right hand side, true or false, does not matter, or that they both are true. Equivalence holds when they both have the same Boolean value, so both of them are true and both of them are false. Then we have also three definitions here for tautology, contradiction, and satisfiability that are very useful. So tautology is a formula that could not be falsified under any interpretation. Contradiction is quite the opposite, so it holds under no interpretation. There is no interpretation in which contradiction formula is not falsified. And the satisfiable formula is one for which there is some interpretation, at least one interpretation, that says that this formula holds. Even though propositional logic is basically much easier and more intuitive to work with compared to truth tables, it is still not expressive enough to state many things that exist in the real world and we might want to model. For example, A is a student is a propositional statement. It can be either true or false. We can describe it by propositional logic. However, consider a statement that talks about a set of individual objects that have a certain property in common. For example, all the integers that are greater than 1 are smaller than their square value, or every student must study 2FA3. So when we have such requirements to formalize, we use predicate logic, which is an extension of propositional logic and allows to use functions, predicates, and quantifiers. A predicate is like a property that we express with a symbol, and we can say that a specific property holds for some object and does not hold for another object. For example, we can define a property like S, Sx, that is true if x is a student, and it's false if x is not a student. So talking about a set of people, like a class of people, we can say if Bob is a student in that class, we can say S Bob is true because he's a student, and if Alice is the instructor, then we say S Alice is false because she's the instructor, not a student. So basically having predicates enable us to talk about a set of objects that have certain properties in common or not. And then we can quantify over those objects or those sets. So each quantifier, existential or universal quantifier, has a scope. In this formula, for example, you can see the scope of this external universal quantifier, and then you can see also the scope of this existential quantifier. So this is just an example to show you that each quantifier has a scope. We can have in a predicate formulae, we can have something like this. So for all x, certain a property holds. So px, for example, holds. Or we can say something like this. So this is one scope, and then we can say, and then there exists x for which some other property holds. So we have two separate scopes of x. Both of them are using notion of x, which is like the variable, but they are not influencing each other because they are two separate scopes. And unlike these two, which are one is integrated in the other one. So these are acceptable forms of formulae in predicate logic, as we'll see in the syntax in the next slide. But we cannot have, or we can also have something like for all x, px, and then qa, a being an individual object. But we cannot say something like this. So this is some property on y being, or x, whatever, being a variable which is not bounded to anything. So here we don't know what y is. Did we mean some y or all y's, or what did we mean here? So we cannot have, in a well-formed predicate formulae, we cannot have free variables that are not bounded to any quantifier. Okay, so let's see the syntax and semantics of predicate logic. A signature defines symbols, base symbols, set of functions, and set of predicates. And then alpha assigns arities to functions and predicates so that we can have one-place predicate, two-place predicate, etc. The same thing also for functions. Every term is made of base object symbols, variables, or functions defined over a set of terms. Each atom is defined as a predicate applied to one or multiple terms, and then formulae are made from atoms or from simpler formulae combined with logic connectors and quantifiers that do not allow for free variables. Now let's see about semantics. So given that functions map variables to objects of the domain that we are modeling, an interpretation of a formulae maps functions to an object and maps predicates to a Boolean value, true or false. So a model made with predicate logic formulae is defined by a pair of its domain and its interpretation. And it is essentially an assignment of semantic values to every expression in the language. So each expression has an interpretation in M, which we show like this. And the semantics are defined as described here. So for a model over, so if you have a model that describes a certain phenomena over a domain alpha 1 to alpha n, this is alpha, what an interpretation does is that it creates a table of predicates, so P1, P2, and then it says which of these objects render each predicate true. This is P2. So for example, alpha 1 and alpha 2, and then for this one it's alpha 3 and alpha 4, and so the same thing for all predicates. So each predicate over a set of objects in M is true only if interpretation of M, which is I, says that those objects make P true. So all those objects are actually here in the interpretation of that predicate. Then for the universal quantifier, this is true. So this expression is true under M only if the interpretation of phi in M for every value of D assigned to X holds. And then existential quantifier here, this one holds under M if the interpretation of phi in M for at least one value of D assigned to X holds. And then we have the other regulations that are more or less like what we've seen for propositional logic. There are different examples of predicate logic, including first-order logic, which is its leading form, and many-sorted first-order logic and second-order logic. There are also higher-order logics that we will not discuss in this lecture. In first-order logic, we have one universe of objects that we call sort, and universal and existential quantifiers range over that sort. Any first-order model consists of a sort, relations, and functions between its elements, and its distinguished constants. So let's see a couple of examples of using FOL formulae to describe a certain requirement. Here we have given a word over alphabet I, and A is a symbol of alphabet. So we have an alphabet, A, and many other things. Let's just assume that it's only A and B. So every acceptable word over this alphabet, if we have no other constraints, would have been empty word, or sometimes we show it by epsilon, A, B, A, B, B, A, B, and any combination of A and B, really. And the question says that we also have a predicate that says for a word W, like for example this one, BAB, predicate A works like this. So it has position 0, position 1, and position 2, A0, A1, and A2. So for position 0 we have B, so predicate A is false here. And then in position 1 we have A, so this is true. And then in position 2 we have B, so this is false. Okay? So this is the definition of the predicate. And the question asks for a formula that is true for every word that has A, so the symbol A, as its first symbol. So the question is asking for a formula that gives us a subset of these possible words. And in that subset, some of these are not acceptable. For example, empty word is not acceptable because it says that every word has A as its first symbol. So the word cannot be empty. It needs to have at least one symbol. And then all those that start with B are not acceptable. So those that start with A are acceptable. So from this part of the question, we understand that we are looking for words in which at least we have one position, and that position is 0. So there exists, position 0 exists. We don't have empty words. And that position is occupied by an A. So this is true for that position. We could also simply write A0, right? So basically, this is the answer. Now, let's see what the second part of the question asks. The second part says, now assume that we also have a function, successor x, which states that position y comes right after position x. So if we have w ABB, then we have positions 0, 1, and 2, and successor of 0 is 1, and successor of 1 is 2. We're not given the definition of this. We just are allowed to use it in our final formula. I mean, the definition is described here, but we don't have the formal definition of it. Describe a formula that holds for every word in which every A is followed by a B. Okay, again, assume that we didn't have these constraints. So what are other possible words over alphabet I? So we could have BB, ABA, BAB, or any other thing. So we want a word where A is followed by a B. But here we don't have an A. So that is still an acceptable word. Here we have A that is followed by B. So this part of the word is okay. But then we have an A that is not followed by anything. That's a problem. So this is not acceptable. Then this one is acceptable because we have only one A and that is immediately followed by B. So this one is acceptable. So how do we define this? So the words in which we don't have an A are acceptable here according to the description, natural language description. So we say the formula we want to write is depends on if there is a position in which a symbol A appears. So if we have a position in which A appears, then we also should have one position right after A. So Y is successor of where A appeared. And we want this to express that position Y is occupied by B. And we have this predicate AX. So we can also define like an additional predicate that says, or we could also here put X, just not to be confused. So we have AX that says if we have an A in position X, and then we have BX or BX that says if that is true only if in position X we have B. So a similar definition to what the question gave us. And here we add this. So we are looking for all words in which, for all positions, this constraint holds. If that position is occupied by A, then there exists another position right after X that is occupied by B. Many-sorted first-order logic is the generalization of first-order logic, where instead of only one sort or one universe of objects that we want to model, we have more than one. And this single change makes many-sorted first-order logic much more applicable for practical scenarios. Any many-sorted FOL model consists of non-empty sorts, relation and functions between their elements, and their distinguished constants. So basically, the definition of many-sorted FOL models is different from FOL models only in the first part, which we have a set of sorts instead of only one. We switch from propositional to predicate logic to have more expressiveness. But even predicate logic has some limitations, and that is why we have higher order logics. Second order logic is an extension of FOL that allows for defining quantifiers over predicates. For example, FOL can state that A has property P and B has property P, or all elements of a set S have property P. But it cannot describe that there is a property in common between A and B. To formalize requirements that look like the latter, we use second order logic. The formula on the slide states that there exists a property and we don't know what that property is. We just know that it exists and it is true for both objects A and B. Let's see a couple of exercises to better understand the differences between FOL and SOL. Okay, so let's see the example. Try to write the statements below in both FOL and SOL, given that A and B are elements of a limited set of geometric shapes. So we have a set in which we have A and B. So first we want to write that A and B have the same shape. And let's try to write it with first order logic. So we can define three predicates: rectangular, triangle, and circle. And so statement A says that we want them to have the same shape. So or both of them are rectangles, or both of them are triangles, or both are circles. And we can write it like this. RA and RB, so both are rectangles, or both are triangles, or both are circles. So this is FOL, but this is in case that we know in advance these predicates, and also there are only three here. What happens if we have 100 of them and we don't even know what they are? In that case, we need to use second order logic. So let's see how we can write it with second order logic. So we can actually keep these three predicates. So the third one was CX. And what we can do is that to define a new predicate called shape, that is defined over R or T or C. So this tells us if the property that is here is actually a shape or not. So it defines a property which is common between these three predicates. And for that we can say, so there exists a property, we don't know what that property is, but we just know it characterizes a shape, and that shape actually holds for both A and B. Then this closes. So this is second order logic formally, where, well, in practice, for a situation like this, we have no choice but use second order logic, because in a realistic scenario, there's no way that we know in advance what are all the predicates that can be defined over the set of elements that we have, that it was A and B. Okay, so let's move to the second part. So the second part of the question asks to state that no object has every shape. Again, we had three predicates, so we want to say there is no object X that has all shapes, so is a rectangular and also a triangle and also a circle. So we do not have that. And again, we can write this only if we know all these predicates. But if we don't, then we already defined a predicate over these predicates, which is called shape, so we can just use that. We say there is no object for which all the predicates that are actually shapes, all of them hold for X. So there is no X for which all predicates that are stating a shape hold for it. Again, this is first order, this is second order. There are other possibilities to add to the expressiveness of propositional or first order logic. Modal logic is one possibility. Up to now, everything was super Boolean, so a sentence was either true or false. Modal logic quantifies the truth of sentences from different points of view. Take for an example this sentence: students like logic. We can elaborate on this sentence with additional information about students liking logic or not. For example, we can say students necessarily or possibly like logic. This aspect of truth evaluation are studied in a subset of modal logic that is called possibility and necessity logic. We can also talk about the students being permitted or obliged to like logic, which opens the modal logic. Or we can add some time requirements to this sentence and say students used to like logic in the past, not anymore. Or they don't like it now, but they will in the future when they learn more. Possibility and necessity logic is sometimes used interchangeably with modal logic because of the two additional operators that modal logic uses, which are pretty much the same as possibility and necessity. So box A means A necessarily happens, and diamond A means A possibly happens. And then in different contexts, they are being perceived as slightly different. So all those different types of modal logic are each very vast and very interesting. But here we follow the lecture only by some indications on temporal logic, in particular linear temporal logic or LTL, which follows the simplest interpretation of time among many other that are more complicated. For example, we have other notations that treat branching time and not linear time. But here we will see only LTL. Basically, LTL formulae are the same as first order logic formulae, except that we have also additional temporal operators. We have next, eventually in the future, always in the future, and until. We interpret this formulae over a bounded time interval, and sometimes it's not even bounded. And each state of the model corresponds to a time instant. So we can say interpretation I of formulae in a model of a system is actually in a snapshot of the system in a certain time instant. In LTL, we have a certain notion of now, meaning the current time instant and the other operators are defined according to their position with respect to now. For example, operator next holds at the state immediately after now. Look at the diagram here. Next phi means one time instant after the point on which we are, which is this one now, where we are evaluating the formula, phi holds. So we are evaluating the formula here, and next phi means that phi holds at this point. Eventually phi means that at some point in the future from now, phi will be true. So now is here, and at some arbitrary point in the future, phi will be true. Always means that phi will hold from now on and always in the future. So if you're evaluating the formula here at this point, phi starts to be true from here, and it will remain true for the rest of the time. And phi until psi means that phi holds from now up to some point in the future in which psi holds. As for syntax and semantics, a well-formed LTL formula follows the rule written in point 1. The time is bounded from left and infinite from right, but sometimes we consider bounded time intervals, so it's bounded from both sides. A sequence of states called sigma entails an atomic proposition if it holds in state 0. Sigma entails negation of phi if and only if it does not entail phi. It entails conjunction of phi 1 and 2 if it entails any of them separately. Sigma entails next phi if and only if at some state starting from state 1 phi will eventually be entailed. And sigma entails eventually phi if there is some state of the formula that entails it at some point. And it entails globally phi if and only if starting from any state phi is reachable. And finally, it entails phi 1 until phi 2 if there is some state from which phi 2 is reachable. And from some state before that, phi 1 was entailed. So LTL could also be simply used with propositional logic. So without predicates, basically. But obviously, that is only useful for simpler examples. Let's see the following example. An essential property for a traffic light with only green and red lights is that the green light appears infinitely often. So starting from any point in time, at some point in the future, we want the light to turn green. So at each point, eventually green light or diamond green light. And then since we want this to hold for all the time instants, then we add a globally or a box operator on its left. But let's see a more realistic example that actually needs first order logic notation. The question asks for modeling the opening and closing a safe box. The question gives us some indications about the requirement that should be formalized. Opening and closing alternate, meaning that we cannot open an open door. So if the first action is opening, the second one will be closing. The model is considered over a bounded time interval from t1 to tn, and closed t and open t are two predicates defined over time instant t that state that actions of opening and closing the door, or the safe in this case, close and open cannot be true at the same time. The initial state is that the safe is closed, and when the action of closing occurs, it means that at some time in the past it has been opened and never closed after that point. So the first formula says that at any time that action close occurs, let's say at t, then there is some time before t, called t1 for example, that the door has been opened and it has not been closed since then, meaning that for all time instants between the last open and the current close, no other close has occurred. The second one says that when open occurs at t, then at some time in the past it was closed and no open occurred since then, or that the initial state or the initial setting has not been changed and so the door was always closed and this is the first time we are actually opening it. In this lecture, we talked about informal, semi-formal, and formal languages, descriptive and operational prospects, and we also talked about logic from propositional logic to predicate logic, and then modal logic. We saw examples of predicate logic including FOL, MSFOL, and SOL, and we also saw LTL as an example of modal logic. I hope you enjoyed this topic. Thank you.